Okay, thank you for this nice introduction. I'm Guusje van Schaik. I'm a fourth-year PhD student at the Leiden University Medical Center, and today I will present some work for my PhD, which I actually did in Strasbourg last year. And it's about the monitoring of conformational heterogeneity of monoclonal antibodies, and we do this by coupling cation exchange chromatography with collision-induced unfolding. So monoclonal antibodies are proteins that can have a variety of different modifications, and it's important that every single modification can impact the higher order structure differently. And in this way, it can also result in an altered functionality. If we talk about therapeutic monoclonal antibodies, this can mean that the product has a different efficacy or stability, making it very important to be able to monitor these modifications and also their impact on conformation. So a tool to investigate conformation of proteins is ion mobility. It was already briefly mentioned before in the pitch, but here we use a slightly different approach. We use the SynapG2, and here the ion mobility cell is located after the quadrupole and before the time of flight, and it's filled with a background gas, which is often either helium or nitrogen. And when your proteins go through this cell, they experience different collisions with the gas molecules. And because of these collisions, or the number of these collisions, we get a separation based on size and charge. So if you have a more open conformation, you will have spend more time in the drift tube or in the ion mobility cell, and then you will have a larger drift time. Compared to closer conformations, they will have a shorter drift time. By the use of different calibrants, we can convert these drift times into collision cross-sections, which can tell you something about the shape of your protein. So it's like shining a lamp on a protein and you see the shadow below. This is a 2D projection of the 3D structure of our protein. Ion mobility is very nice to get a global overview of your protein. However, if you want to look into minor modifications or what their impact is on the conformation of the proteins, it is not sensitive enough. Therefore, we use another technique which is based on ion mobility using the same machine, but it's called collision-induced unfolding. And here we increase the voltage in the trap before the ion mobility cell. So in this example, we increase the voltage from 0, which is the ground state, as we also measure with just normal ion mobility, to 200 volts, where you can already see that the protein gets unfolded. If we represent this data in another way, we get a CIU fingerprint, as we call it. And here you can see the different states of the protein and the unfolding of the protein. So in this example, we have the ground state, with a particular drift time, and when we increase the voltage, at one point we get to another conformational state and then to a second one. And using this technique, we can pick up very minor differences in protein conformation. Therefore, it's very useful. However, there are also some disadvantages when we use it in a classical way. For instance, you need to buffer exchange all your samples prior to the measurements, because there cannot be any non-volatile salts present, because it's a direct infusion approach. Also, the collection of the data is quite time consuming, since you have to increase the voltage manually. And also, when you have properties, or when you have proteoforms that have a similar mass, you cannot record them separately, because you will get an average fingerprint of all these species together. Therefore, we thought it would be very nice if we can have a separation, a liquid separation up front, so we can deal with all these disadvantages and still get this nice collision-induced unfolding. So first of all, it was very important to select a liquid chromatography mode that has native conditions. Since we want to maintain or measure the conformation of proteins, we cannot induce any denaturation of the proteins during separation. Since monoclonal antibodies are known to have quite some charge variance, we chose cation exchange chromatography to separate based on charge or isoelectric points. And you can make this method MS compatible by using volatile buffers such as ammonium acetate. And elution can be accomplished either with a salt gradient or a pH gradient, but recently it was shown that the combination of both is the best for monoclonal antibodies. So how does it work? Well, we inject our proteins, and then we increase the pH and salt in the column, and one by one our proteins or proteoforms will elute, where you have the first peak has the lowest isoelectric point and the last peak the highest isoelectric point. To be able to couple these two separation techniques together, we had to adjust the methods quite a bit, because normally for liquid chromatography, you would like very narrow peaks. However, if we're going to perform collision-induced unfolding, we actually like broad peaks. But they cannot be too broad because then the signal is too low, so you need to find a compromise over there. Also, you want to apply as many different voltages in one run, because it means you have less runs to measure, and it means that it goes faster. We found eventually that we can apply 4 different voltages in one run from 0.2 minutes wide, and then we get sufficient MS signal to get a reliable fingerprint, and we reduce the number of time we need to get a fingerprint. So in total, we need 4 cation exchange measurements to obtain a fingerprint from 0 to 150 volts. We then wanted to compare if our separation dimension induces some changes in the conformation by comparing it to a conventional approach, which uses direct infusion in an electrospray source. Here you see the data of middle of trastuzumab. And even though we see some differences in the fingerprints, the overall key voltages or the key features, they are quite similar still. So then we continue to look a bit more at if we could see differences by inducing a small, or by adding a small percentage of acetonitrile to the mobile phase, because normally this is not considered as native conditions anymore. So we compared the fingerprints of intact trastuzumab here, and even though yeah, we can see already some differences, some similarities, but I think if we look to the arrival time distributions, you can see it even more clearly, that especially for the first few voltages, the conformation of the mobile phase without acetonitrile has a lower drift time compared to the conformations with acetonitrile. Interestingly, if we go a bit further in the fingerprint, so up from 70 or 80 volts, the arrival time distributions completely overlap and there's no influence anymore. So we applied this workflow already for a mixture of different antibodies. We chose 3 from different subclasses with a difference in PI but similar masses. And by using our CEX-CIU approach, we could collect data of all 3 antibodies in one run, which means we could obtain 3 different fingerprints with only 4 cation exchange runs. And you might think, why would this be useful for different monoclonal antibodies? Well, nowadays there are more and more therapeutic products that have co-formulated antibodies, and in this way you could analyze them at the same time in the same run by separating them. So finally, I would like to conclude by showing you this toolbox we made. Actually, I think this is a very elegant way to characterize monoclonal antibodies because a lot of different properties are encountered. So first we use cation exchange to resolve different charge variants, but it also allows to detect minor populations such as deamidation, which you can separate with cation exchange. Then we use native mass spectrometry for the assignment of the different proteoforms because we can detect their masses. Using ion mobility, we obtain collision cross-sections, and this gives an idea about the global conformation. And finally, we use collision-induced unfolding to monitor the unfolding of these proteins in the gas phase, but also to reveal minor structural differences. Currently, I showed just one application, but we're also working to show it on other applications where we investigate proteoforms after thermal stress, of also the impact of glycosylation on conformation and unfolding. So finally, I would like to thank the Leiden University Medical Center, where I do my PhD, but also Strasbourg, where I went to perform all these experiments. If you have questions, let me know in the Q&A session.